Today we're going to discuss heme biosynthesis, regulation, and degradation. So, essentially, heme is an essential component of myoglobin, hemoglobin, and cytochrome proteins. The structure here is on the left. It is a central iron atom situated within a porphyrin ring, coordinated by nitrogen atoms here. There are four outer chiral rings linked together by methane bridges that are completely formed by glycine and acetate derivatives, and although acetate is first converted to succinyl-CoA before biosynthesis. Here, we see acetate being a source of succinyl-CoA as it travels through the citric acid cycle. On this left, we see filled-in squares and circles representing current rounds of the TCA cycle, and open symbols represent previous rounds, and basically it shows that acetate forms the carbon atoms and oxygen atoms of succinyl-CoA over time. The actual pathway of heme biosynthesis, glycine and succinyl-CoA start the pathway of heme biosynthesis. A pyridoxal phosphate, vitamin B6 intermediate, catalyzes breaking of succinyl-CoA's carbonyl group, leading to succinyl-CoA leaving and a glycine alpha carbon bond formation. This forms ALA, which is here at the bottom of the slide, which then leaves the mitochondria and interacts with porphobuinogen synthase. The mechanism of porphobuinogen synthase is still somewhat unknown. We don't really have a curved arrow mechanism, but we eventually see the conversion of ALA to this porphobuinogen ring product. Importantly, we have a D3 symmetric group hexameric complex, which has low activity, and we also have a D4 symmetric group octameric complex with the enzyme, which has high activity and is favored by high protein and substrate concentration and is favored at physiological pH. This octameric complex shown in the bottom forms this hugging dimer where these alpha-beta barrels are interacting, and the hexameric complex's N-terminal arms are extended away from the core, forming this detached dimer with reduced activity. The final product is this BPG ring that will be used as a structural basis for heme. BPG interacts with dipyromethane in complex with BPG deaminase, the enzyme, to catalyze formation of BPG tetramer. This is called methylbilane, and then interaction with water forms hydroxymethylbilane. We have two possible products. We have uroporphyrinogen 1, which is a symmetric product. We don't want it because heme is non-symmetric. We don't use this product. Or we have uroporphyrinogen 3, which must be utilized in order for heme to form, and the use of uroporphyrinogen synthase 3 synthase ensures formation of the unsymmetric product over the symmetric product, and heme biosynthesis can continue. Now we skip ahead a few steps to the final ring formation reaction, ferrochelatase, which essentially just adds the iron atom to the already formed porphyrin ring. This is an ordered bye-bye mechanism, so iron 2 binds to the active site first, and nitrogen molecules on the porphyrin ring of protoporphyrin 9 are deprotonated, which is hypothesized to be abstracted by histidine 263 and ferrochelatase, and then iron coordinates with the porphyrin ring, forming the heme product in these four nitrogen ligands. And we see that the enzyme is regulated by a distant iron 2 sulfur cluster, which binds the C-terminal extension to the N-terminal domain, and residues in the histidine and related residues cause a loss of activity. Now let's quickly take a look of the enzyme itself, ferrochelatase. This is the ferrochelatase dimer protein. The substrate binds in a pocket that somewhat excludes solvent. There's less of these red things here, and I have the histidine 263 highlighted in blue, and there's a distal 2 iron 2 sulfur cluster on the other side of the substrate binding pocket that is known to have a catalytic use. Now let's move on to some heme regulation. So heme is synthesized primarily in erythroid cells in the liver. Erythroid cells account for approximately 85% of total heme production, with synthesis occurring during differentiation to support hemoglobin production. Once mature, erythrocytes aren't really making any more hemoglobin. So consequently, the heme produced during differentiation must sustain these cells for their 120-day lifespan. In contrast, the liver contributes around 12% of total heme production, and this is primarily for cytochrome P450 enzymes, and synthesis is tightly regulated to meet fluctuating metabolic demands. In the liver, heme regulates the formation of the ALA intermediate, if you remember, so the first reaction in heme biosynthesis. Through feedback inhibition of mitochondrial transport, and repression of enzyme synthesis. However, in erythroid cells, heme stimulates protein synthesis in reticulocytes, promoting the coordinated production of hemoglobin subunits. And biosynthesis is primarily controlled here by ferrochelatase and porphobuinogen deaminase activity, along with iron availability, so not the same